Hello, we continue solving problems on the application of the law of universal gravitation and will solve the next mice. Or problem. Three masses of 6.75 kilograms each are located at the corners of an equilateral triangle located in space away from any other mass. If the length of the sides of the triangle is 1.25 meters, find the magnitude of the total force acting on each mass. So here we are going to look at the interaction of several objects using gravitational forces. And we know that each body has a mass of 6.75 kilograms. And we also know that the distance between each mass, which is this, the length of the side of the triangle is 1.25 meters. How to solve such a problem? Of course, the first thing to do is to draw a picture that shows us how these objects are located. So we have three bodies that have equal masses, and they're located in angles of an equilateral triangle. M, M, and M. The length of a side of the triangle is R, showed. Well, now the question arises how to determine the force that will act on each of these objects. Here it will be clear that each pair of these bodies will be attracted to each other with certain forces, and it turns out that each body will be acted upon by the other two bodies with certain forces that will be directed along the sides of the triangle. So it turns out that, for example, if you and I look at the top object, we'll be acted upon by a force from this mass. It will be, for example, force 1, and there will be a force of 2 on the side of this mass. Let's take this vector as acting along this side. So it turns out that you and I now have two forces acting on this object, and then the resultant force is the vector sum of these two forces acting on this object. Let's write that down as an equation. So now our task is to sum these two forces and see what the result of this summation will be. To do that, we use the rule of vector addition with a parallelogram. That is, we add it up to a parallelogram and we get the resultant vector, which will be directed to the center of this triangle. Given that these forces are modulo the same, we have in fact rhombus, that is, this figure will be a rhombus, and the diagonal of the rhombus is just the force that are going to determine. Now our task is to calculate the diagonal of this rhombus, because we have done everything from the point of view of the vector equation. Now we move on to the geometric part of this problem. So how to find the diagonal of the rhombus? What do we know for this? Well, first of all, we know that the angle between the two forces F1 and F2 is 60 degrees. Let us show it. This angle is 60 degrees. But then it follows that the angle that's obtuse will have a value of 120 degrees. This will help us to calculate the diagonal, which is simultaneously one of the sides of the obtained triangles. If you and I consider a triangle that consists of a force F1, the second side is the force F2 because we used parallel transfer, and the third side is the resultant force. And then it turns out that we have three forces in this triangle and an angle inside this triangle. This problem can be solved using the well-known cosine theorem, which allows you to find the unknown side of a triangle from two known sides and the angle between them. This is the most convenient theorem that suits this situation. So the resultant force is then found to be equal to the square root of the sum of the squares of the two remaining sides, which is F12 plus F22, minus their doubled product of F1, F2, and the cosine of the angle between them, which in this case is 120 degrees, all by the sine of the root. Also, we know that the forces F1 and F2 will be equal in modulus, given that all the masses, once again, in this figure we have the same, and the distance also has the same value, so the forces will be equal to each other. Then it turns out that we will write down the resultant force by a simpler formula. Here we get the sum of two identical forces. Let's say it will be 2F12. Here we also get the product of identical forces. We can also write it down as F12. And the cosine of 120 degrees, unchanged. Now we can take the value of F1 beyond the root sign. It goes from the root to the first degree. And here we can take the common multiplier out of the parenthesis as 2 multiplied by 1 minus the cosine, 120 degrees. So in simpler form, the expression can be written like this. And then we need to write down here the formula for calculating the force of attraction. And you and I have a final formula that we're going to use to do the further calculations. Now I'll point out why mass is squared, because as I said earlier, here we have the product of two masses, and given that they are equal in value, we get the square of these masses. So we've got a value for this force, which is the formula, and now we have to calculate what it's equal to. So 6.67 times 10 minus the 11th degree, then 6.75 squared, divided by 1.25 squared. And here we have everything unchanged. After the substitution, we've got the approximate value of the interaction force. 3.4 tenths of 10 minus to the 9th power of Newton. Well, the expected interaction force will be small because, of course, the masses interacting also have small values. The distances are basically small. So, of course, the answer is going to be small. But nevertheless, you and I have seen how the superposition principle is applied in practice. So you can use this methodology to solve the same type of problem or more complicated if there's more bodies involved. That's all for now. Goodbye.